let's move forward to finish the linear algebra. So we talked about basis already, right? We talked about that. For example, we talk about V equals to AX hat plus BY hat plus CZ hat. And the basis vector are the X, Y, Z, right? So in a general situation, you have multidimensional, you have the basis vectors. It can be x0, x1, all the way to xn minus 1. So this is an n-dimensional space, right? So if xi, xj equals to 0 when I not equal to j, equals to 1 when I equal to j, then we say that this is an orthonormal basis. So what does it mean? When I equals to j, it means it is the same vector. For example, I'm talking about x0 inner product with x0, x5 inner product with x5. They give me 1. It's just like x dot x, x hat dot x is 1, y dot hat dot y is 1, right? C hat dot C hat is 1. They are orthonormal. They are normalized, right? They are normalized. This is the what we call, this is normalized. So this is a very important thing in the quantum computing. We only deal with the normalized vector. It means their length is 1, because remember what is the x inner vector dot is, a basis vector inner product with itself is just the length square, right? By definition, right? And it is 0 when they are not the same. It means, again, what is inner product? We're talking about how much is the common part of it, right? So this means that they are orthonormal. Orthogonal. I say the wrong thing. Orthogonal, right? It is orthogonal. Right? In 3D space, it's easy to understand. They are just perpendicular to each other. They don't have common part. Okay, so we will deal with this type of orthonormal basis. Now, this is very useful because it simplifies our life a lot. Now, for example, no example, but then let's look at another thing. We also can talk about normalized vector. It's a general vector. For example, if V equals to A0, x0 plus all the way to an minus 1, xn minus 1, right? If V inner product of V equal to 1, then this is a normalized vector. Right, so that's nothing special. It's basically like in 3D, a dot a equal to 1, then its length is 1, right? Okay. But why this is important in quantum computing or mechanics? What is V dot V? V inner product with V. So I'm going to use the matrix form, right? You can also use this expression to do that, but I'm going to use the matrix form. This equal to A0 star, A1 star, all the way to an minus 1 star. I hope you are very familiar with this notation now. A0, A1, all the way to an minus 1, right? This is just a matrix multiplication, and what do we get? A0 star A, 0, plus A1 star A1, plus all the way to an minus 1 star an minus 1. Do you see this? Because this multiplied by this one, plus this multiplied by this one, plus this multiplied by this one, right? And this is just equal to A0 squared plus A1 squared all the way to an minus 1 squared. And we say it equals to 1 if it is normalized. If it is not normalized, it's not equal to 1. But we say all vector we're doing in quantum computing must be normalized. Why is that? Because if I do a measurement on V, right, it's going to collapse to one of the basis vector by, as we have discussed, right? One of them, right? The simple case is just spin up, spin down, right? So what is the probability of collapsing to any xi, any one of them? What's the probability of collapsing to any one of them? It must be either collapse to 0, which is A0 squared, or AX1, which is A1 squared, or AXn minus 1, which is AN minus 1 squared, right? So you have, it's just like you have five choices. What's the probability of picking one of them? Sum of all the probability, right? And it must be 1. I always will pick one of them, right? And that's why this makes sense, right? So all the vector in quantum mechanics, you need to be normalized. If it is not normalized, then I have larger than 1 or less than 1 probability of getting all the possible outcome, which is not the daily life experience, right? And you go back to the spin, you say, okay, you measure it, either get 0 or get 1. What is the probability of getting 0 or 1? Of course, it's the probability of getting 0 plus the probability of getting 1, and it must be 1, right? So that's why we want to have a normalized vector, right? So for this slide, the important thing is to understand there's something called orthonormal basis. That is the definition of orthogonal and normalized. And the other thing is we are interested in normalized vector in general. Okay.
It is quite close to ideal, that one, but in practical, probability may not be equals to all this one.
No, it needs to be 1. When you do measure, you either or. You can say in practice, the wave function might not exactly what you write down, right? But if it is this wave function, you measure it, you will always collapse to 1. I'm not correct. You always will collapse to any of this. And the probability must be the sum of the square of their coefficient. And that needs to be 1. Now think about that. If I tell you, you will always get something among this possible choice. The probability of getting one among this choice is 1, right? Right, okay? Now then we talk about the basis, then let's talk about how to change the basis. This is very important in quantum computing, because if you work in the right basis, it makes your life easier, and also it can help you to do some manipulation, right? So I want to talk about some very simple example, like what I said last time. I bought 12 eggs from the supermarket. I can say I bought 12 1/8, or I can say I buy 1 dozen egg, right? So both of them are the same, but they have different bases. One is 1/8, one is 12/8. Okay? So now I have a vector here, right? You see that I have a vector here. What is the vector in general? I am going to talk about in general. I can have two different bases. I just have this 2D plane. I call that I have two bases set. One is 0, 1, and other is plus and minus, right? So I have a basis set which is 0, 1, Maybe you are still confused, right? What is the meaning of this cat notation of 0, 1? But then you just step back. It's just like saying that what is the notation of x hat and y hat? The 2D plane is spanned by x hat and y hat. And now I don't call it x hat and y hat. I call it 0 and 1 in the cat. But the reason I call it is that I'm not going to only talk about the 2D plane. I'm going to talk about something very abstract, like egg, apple, as the unit, right? So in this basis, I will say psi, this is given, right? I just given in general, equal to alpha 0 plus beta 1. Again, you can think about equal to 2x hat plus 5y hat. That give you the vector, right? Now, how about in the basis of plus and minus? Do not care about what is the meaning of plus minus or if it is valid. Now, you see that it's just I rotate the coordinate by 45 degrees. I want to represent in that way. It's just like I want to call the amount of egg I bought in terms of dozen instead of egg, number of 1 egg, right? So in that case, how can I change the basis? This one, I'm going to say this is also equal to alpha beta, right? But when I say alpha, I mean I have alpha part of 0, I have beta part of 1. For the same vector, how about that? What is that, right? So I can do substitution. This is not difficult, right? What is 0 in terms of plus and minus? Just by geometry, this is 0. I go down by 90 degrees. Here I go down by 90 degrees. I will see that, right? You prove yourself. This is just equal to the square root of plus minus. Agree? Yeah. The details, the number, you might not be easy to see, but just do some trigonometry, you find that. But you definitely agree that it is the sum of these two vectors, right? And similarly, 1 equals to 1 over square root plus minus minus, okay? If you don't agree, look at this, because this plus is, where is that? Yeah, this 1, right? You are going to take the negative of minus if you do the projection. But anyway, then it means I can represent this psi in this way. Equals to alpha 0 plus beta 1. Now I substitute equal to, because 0 is square root of plus minus. And then beta is, 1 is 1 over square root plus minus minus. So I am basically done. It's just a very simple algebraic substitution. And I regroup the terms. This equal to plus is 1 over square root. I have alpha plus beta. Just group the terms. And then alpha minus beta. Okay, as an example, for minus, I have alpha 1 over square root plus minus beta 1 over square root 2, right? So this is 1 over square root 2 alpha minus beta, right? How about in the matrix form? I can write it as this, alpha plus beta, alpha minus beta. Again, for the same vector, I have different matrix form. The reason is because I'm using different bases. Now I'm saying that I have alpha plus beta divided by square root 2 amount of plus. And this is minus. Right? It's just that for the 1D example about this number of apples or egg I have bought, I'm going to write this as 12, but 1 egg as the basis. And this is as 1, but 1 dozen as the basis. Okay? Now, this type of skill you need to practice, but just be careful, it is only a pure substitution. Now, to change the basis, we will talk about the transformation matrix, because It's not always trivial to see the relationship, right? And we'll use the transformation matrix we discussed later. At that time, you just trust me the equation. We won't derive it. But this is the fundamental understanding. If you later you get lost, think about this. This is fake, but it's a good way for you to map to anything that is confusing you. Okay. So here I have a caveat, right? It turned out that in qubit, this relationship are correct. I just told you 0 equal to plus minus over square root 2. This relationship are correct. But this picture is incorrect because the qubit does not live on the 2D real plane. It lives in a 2D complex plane. Because in this plane, all the vector can only have real coefficient. You only can have psi equal to 5, 0 plus 1, 1, right? But in the qubit space, you can have psi equal to I0 plus 1 minus I1. Okay? So this is something can help me to memorize this equation and appreciate some of the fundamental in coding the Heisenberg uncertainty principle if I want. But this is not the real thing that we are using. I just want to warn you about this. But this equation turned out to be correct. But what is plus, what is minus, what is 0, what is 1? We will explain more later when we go to the broad sphere and map it to the physical qubit. Okay? We are done with the elements, right? We do have the vectors. Vector is the most important, and the definition of inner products gives us a Hilbert space. But this is not interesting. The interesting is that we can manipulate the vector. We are going to rotate it. This is a 2D space, easy to rotate, but it's similar. We can imagine we rotate in a hyperspace that we cannot see. Okay? Now, so how do we rotate them? It is through something called operator. And how do you modify a matrix? Well, modify a vector. Well, besides vector addition, the most important thing is matrix multiplication. You multiply a vector, then you get another vector, right? V equals to a matrix times maybe U, right? You give a vector, multiply, you get another vector. And that is the operator. What it does is to rotate it in a space, right? For example, here we are not going to give general form. I just ask you, how do I rotate V1 who plus? Right? V1, what is the value of V1 now? In terms of the basis vector 0 and 1, what is V1? V1, very good, equals to 0. Right? It's just like saying that V1 equal to x hat. That is what it is talking about. How do I rotate it? Well, to rotate it, the best way is we go to the matrix form. I'm going to write in matrix form 1, 0. Again, I know that 1 means I have 1 part of 0. 0 means I have 0 part of 1. Basically, just like 2D plane, I am x hat plus 0 y hat. Okay. Now, how do I rotate it? I suggest that I can use something called a matrix called H, which you will learn later, the Hadamard gate. But it's just a matrix. It really doesn't matter what it is now. And let's try how do we do the rotation. I apply H to V1. Then I just do my matrix multiplication. This is the minimum prerequisite of this class. How do you do matrix multiplication? Row times column. 1 times 1 plus 0 times 1 as the first element. 1 times 1 negative 1 times 0 as the second element. So this gives me square root of 1, 1, right? And if you remember, we just told you earlier, this is just equal to 1 over square root 0 plus 1, yeah? What is 1 over square root 0 plus 1? It's just plus, right? So this one does give me plus. So I was here, which is 0. After applying this rotation matrix, I come to here, becomes plus. Now this is just a demonstration, right? But quantum computing is just like you try to find the correct matrix to rotate the vector and then do the computation you want. Okay? I'm a little bit fast. Is that okay? Any questions? Similar to image processing, exactly. And actually, it's actually easier than image processing because in image processing, you can have stretch, compression, distortion. Here, you only have rotation. And it's all what we call unitary. It preserves the inner product, which we will talk about that later. It turned out to be very easy in this sense. Yeah. So the point here I want you to remember is now I introduce something called operator, right? And later, when we talk about the hardware, is that how do you implement this operator physically? So let me remind you, right? In a quantum computer, we have the input wave function, a state can be 0, like what we are showing here. And then we go through different type of gates. And these gates adjust the matrix. I mean, mathematically, they are the matrix. Physically, they are the microwave pulse, lasers pulse, right? And then you keep rotating them, right? And eventually, you do the measurement. Before you do the measurement, everything is reversible. Okay? Because we just talking about this is a rotation, like you say in image processing. I can rotate it to the left, then I can rotate to the right? I won't lose the state if I rotate it. I mean, it's reversible. What I mean is, right? Okay. Monday, yeah.